Hello, our warm-up question today is, what are the quantum numbers for the last electron of fluorine? Right. Hopefully, you are able to say that our principal quantum number n is equal to 2, our angular momentum number L is equal to 1, our magnetic number m sub L is equal to 0, and our spin number m sub S is equal to negative 1/2, because the electron configuration of fluorine is 1s2, 2s2, 2p5. If we're going to fill out an electron orbital diagram to help us figure out what that spin magnetic number is, it might also be helpful to know the charge. So it will tell us the number of electrons. So our charge for fluorine is 9. So then if we are to fill out our electron orbital box diagram, it should look like this. Filling our ground state electrons first, and then we are going to maximize unpaired parallel electrons. There we are. So that would mean then our last electron is this one right here. And so it clearly follows that we're in the second energy level, so n is 2. We're in a p orbital, and we know that p orbitals always have an L value of 1. We are in -1, 0, 1. Clearly, we're in the m sub L equals 0, and because it is a downward facing arrow, our spin is going to be negative 1/2. So this is definitely a skill to practice, especially if this was something that took a little bit longer for you to get through, because this is going to be on our assessment on Thursday. But today we're going to talk about periodic trends. So our learning objective is, I can explain why many periodic trends, including atomic size, ionization energy, and electron affinity, occur based on electron configurations. A lot of this today will probably be quite familiar, but we'll be able to discuss it in greater depth because of our understandings about electron orbitals and electron configuration. So let's talk about atomic size. We can define atomic size a couple of different ways. When we're talking about metals, we can talk about a metallic radius, or the distance between the nuclei of two metal atoms that are in a crystal, half of that distance. Similarly, if we have a diatomic atom that is covalently bonded to another atom that is identical to it, half of that distance is called the covalent radius. So those are kind of our two definitions for atomic size, depending on what type of material we're talking about. There are essentially two big trends that we see as a result of the increase in energy level down a group, and then the change in the effective charge felt by those outermost electrons. And those are kind of the two determining factors that dictate how atomic size changes down a group and across a period. So as we see an increase in energy level, we see electrons that are existing further away from the nucleus. And so those electrons are also being shielded by all of those inner electrons. So as we go down a group, we see electrons that are existing further away from the nucleus and electrons that have that are feeling less of a strong pull towards that nucleus because there's so many other inner electrons that are shielding that positive charge. So as we go down a group, due to the change in energy level, due to the increase in energy level, we're going to see larger atomic radii. However, as we go across a period, the effective charge, so that effective pull towards the nucleus, isn't going to be as affected by the addition of electrons because they're being added to the same energy level. So there's not going to be a greater number of inner electrons that are shielding. It's simply going to be more electrons in the same energy level. And therefore, we're going to see a decrease in atomic size as we go across a period, because as we add to the same energy level, those electrons are still going to be feeling the same amount of pull towards that nucleus. And as the nucleus itself gets bigger, it has more of a positive charge, and so it's able to pull those electrons in closer yet. All of this goes to say that these trends exist for kind of like the S and the P block. However, these transition elements are relatively constant in their size due to the shielding effects of those inner electrons. So transition elements are like our metals. Those are going to have a relatively constant size across the period. However, they will still increase as we go down a group. This graph helps us to kind of visualize what I mean by that. So as we go down a group, so if you look from lithium down to cesium, our atomic radius is increasing. However, then if we look across the period from lithium down to neon, we'll see that we decrease greatly in atomic radius. So neon is much smaller. However, we can still see an increase from neon down to radon. We can also see some pretty clear patterns with ionization energy. Ionization energy is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms or ions. And because we are removing an electron from an atom that has a very strong positive attraction to that atom, this is always going to be something that requires energy. So our ionization energy value is always going to be a positive number. This is an endothermic maneuver. This is always going to require energy. And when we're dealing with multi-electron atoms, we can have multiple ionization energies. So this is specifically dealing with the first ionization energy, or the energy required to remove the first electron. And generally speaking, as the size of an atom decreases, the first ionization energy increases. And if we think about this, this makes sense. When size decreases, that means those outer electrons feel a stronger attraction to the positively charged nucleus, and it's going to require even more energy to remove one rather than an electron that exists far, far away, or that tends to exist far, far away from the positively charged nucleus, or that doesn't feel the attractive forces of the nucleus because of shielding by inner electrons. If we look at this graphic, I think this is a nice one because it's got a little bit of 3D stuff going on. We can see that ionization energy is clearly, it definitely increases as we go across a period, and it also decreases as we go down a group. And again, if we think about this, those like francium down here is a very large, very, very large atom with lots of shielding by those inner electrons. So those outermost electrons, they're going to pop off nice and easily. However, if we think of like helium and neon over here, we've got very small atoms that feel very, very close, or that feel very strongly those attractive forces to the nucleus. So they are going to require a much greater amount of energy to remove those electrons. When looking at subsequent ionization energy, so ionization energy 2, ionization energy 3, generally speaking, those ionization energies will be much lower than the first ionization energy until all of the valence electrons have been removed. Once we get to the inner electrons, the core electrons, those feel much more strongly the pull of the nucleus, the positive pull of the nucleus. And so then we're going to see a very steep jump up in ionization energies again once we get to the core electrons, which is why those electrons are not involved in reactions. Electron affinity is another behavior that we can see lots of trends on the periodic table with. And electron affinity is the amount of energy required to, or the change in energy when 1 mole of gaseous atoms or ions absorb 1 mole of electrons. So basically when we ionize by adding an electron and not removing an electron. Generally speaking, in our first electron affinity, we are going to have energy being released. So this is because that electron is going to be attracted to the positive charge of the nucleus. So we can add 1 more electron in there, generally speaking, and energy will be released. It will be exothermic. However, when we hop up to our second electron affinity, or EA sub 2, we're going to require energy because that second electron is going to be battling the repulsive forces of the other electrons. And electron affinity when we're talking about electron affinity, the patterns that we observe aren't quite as cut and dry as with ionization energy and atomic size, because electron affinity is affected by more factors than simply the effective nuclear charge and atomic size. So there are some general trends. These are not regular patterns like ionization or atomic radius. Generally speaking, the first ionization increases in magnitude from left to right. So that means that on the right side of the periodic table, you will have a larger negative number for that first electron affinity. And it generally increases from bottom to top. So the larger electron affinity values are going to be, the most negative electron affinity values are going to be found in the at the bottom of the periodic table and decrease in size as you move your way up. One of these areas on the periodic table where we see trends that don't follow a periodic trend necessarily would be with our reactive nonmetals in group 6A and 7A. So that's halogens and then the group right prior to the halogens. And they tend to form negative ions. If you think about their valence electron structure, that makes a lot of sense. They would fill up that orbital. And also because they are much smaller atoms, that positive nucleus is much more strongly attracting their outer electrons. It's going to be much easier for them to attract and to hold on to those electrons gained. And so they tend to form negative ions. Our reactive metals, so that's our alkali metals and our alkaline earth metals in groups 1A and 2A, they tend to form positive ions because they are so large that the nucleus is not having as strong of an attractive effect on those outermost electrons. So those metals tend not to form negative ions; they tend to form positive ions and have very very low ionization energies and very low electron affinity. And finally, our noble gases tend not to form ions because they have very stable electron configurations. They have full orbitals. They tend not to gain or lose electrons very easily, and therefore they do not form ions. Some other non-periodic behavior, but some other interesting behavior that can be observed and understood better with our orbital knowledge is different metallic behaviors. And one very, very interesting one is the acid-base behavior of metals. So main group metals transfer electrons to oxygen when they're in water, which means that they become ionic oxides and they behave like a base when they're in a water solution. And this metallic behavior increases as we go down a group. And if you think about that, that makes sense. The larger metals are going to have a much looser hold on those valence electrons and more easily transfer them to oxygen. So they're going to be even more basic when they're in a water solution. Non-metals share their electrons with water and they form covalent oxides, and therefore they have very acidic behavior when they're in a water solution. And these become more acidic left to right across a period. So again, these are for non-metals that are covalently sharing electrons with oxygen. They're forming covalent bonds, covalent oxides. And that, again, becomes more acidic the further right that we go across a period. We're going to talk a little bit about our transition metal ions because they are funky. So oftentimes our alkali earth metals, or our alkali metals, or halogens and materials like that are gaining and losing electrons to try to have a more stable electron configuration, to have either a full shell or to empty an outer shell so that they have an electron configuration that resembles that of the nearest noble gas, because we know that noble gases are very non-reactive, they have very stable shells. All of those electrons are pretty equally feeling the attractive force to the nucleus, so they're very stable. Transition metals don't tend to do that. Transition metals behave in their own way, but they do often form cations, and the way in which they form cations is slightly, not counterintuitive, but slightly different from how we would anticipate we should. Because usually when we're talking about a material forming an ion, we're removing an electron or two from the highest energy level and the highest orbital, so the last orbital that we filled. However, when we are dealing with transition metals, so you'll remember, usually we have, this is where the weird filling pattern comes in. We have some number s, and then we have a d orbital, because that d orbital, even though it is of a slightly lower energy level, its actual energy is higher than the nearest, than the next energy level's s orbital. So generally speaking, when we would think that we would form a cation, we would remove them from the last place we put them. We take them out of that d orbital. However, what we're actually going to do is we're going to remove them first from that s energy, from that s orbital. So from the highest energy level, s orbital, we take our electrons to form cations. And then if we are still, so if we're dealing with like a +4, then we will take those remaining 2 electrons from the d orbital. And transition metals, if you think way back, we talked a little bit about paramagnetic and diamagnetic. So paramagnetic materials are materials that have unpaired electrons, because remember, all of our electrons generate a small magnetic field, and paramagnetic materials exhibit an attraction when another magnetic field is presented. And a diamagnetic material is not attracted at all and is slightly repelled by another magnetic field. So transition metal ions, we can see that we're actually removing those electrons from the s orbital because of paramagnetism and diamagnetism. When we observe ions that have had electrons removed from the s orbital and are still exhibiting paramagnetism or diamagnetism, we can see that that is in fact where those electrons are coming from. They're not being taken from that upper d orbital. And so that's one of the reasons why it's important to pay attention to and be aware of paramagnetism and diamagnetism. And finally, let's talk about ionic versus atomic size. So if we compare the size of an atom, an unionized atom, it's going to have a very different atomic radius than an ion of that atom. We call that the ionic radius. So generally speaking, cations are going to be much smaller than their parent atoms, because that positively charged nucleus is going to pull more tightly on a smaller number of electrons. And anions are going to be much larger than their parent atoms, because the attractive force is not going to be as strong, and there's going to be repulsive forces between the increased number of electrons. Generally speaking, the ionic size is going to increase as we go down a group, because we're increasing the energy level. Patterns get a little bit funky across a period. So we're going to see a decrease in the size of cations as we move from left to right. However, when we reach the point where we get to materials that start to form anions rather than cations, we're going to see a very, very, very large size increase. And then as we work our way, continue working from left to right, the size of those anions is going to get smaller as well. And so here, this great little chart is a good depiction of that. As we go down a group, we're going to see an increase in size. As we go across a period, we're going to see a decrease in size, and then a big jump up once we get to an anion again, and then we still continue to decrease. There you have it, ionic versus atomic size. Here's a chart of basic trends across the periodic table. Obviously, this should be taken with a grain of salt. As we just discussed, there's lots of slightly different behaviors that are observed. So generally speaking, ionization energy and electronegativity are going to increase from left to right and increase from bottom of a group to the top of a group. Atomic radius is going to increase as we go down a group, and it is going to decrease as we go across the periodic table from left to right, or conversely, increase from right to left. And electron affinity is going to increase from the bottom of a group to the top of a group, and increase from the left to the right of the periodic table.